Welcome back to the video course on fluid mechanics. In the last lecture in fluid statics, we were discussing about the buoyant forces and then Archimedes principles and related issues. So, in the Archimedes principle, we have seen that when a body is immersed in a fluid, either wholly or partially, it is buoyed or lifted up by a force which is equal to the weight of the fluid displaced by the body. So, this we have seen, and then we have seen that we can equate the force, buoyant force, to the weight of liquid displaced, and then we can apply this theory to many engineering problems. So, the point through which the buoyant force acts is called center of buoyancy, and the buoyant force passes through the centroid of the displaced volume. So, that also we have seen in the last lecture, and then we can equate to the buoyant force to the weight of the liquid displaced. So, that means FB is equal to gamma into the volume. So, this volume displaced liquid. So, this theory we can apply to many engineering problems, and also say equipments like hydrometer, which is used for the specific gravity determination, is based upon this principle. So, now based upon the buoyant force and the Archimedes principle, now we will discuss the stability and equilibrium in fluid statics. So, as we have discussed earlier, the position, a floating body or a submerged body or a body can be either in stable equilibrium or unstable equilibrium or say neutral equilibrium. So, a stability of a submerged or a floating body means the tendency for the body to return to the original upright position after it has been displaced slightly. So, here in this slide you can see that here there in a container there is water, and then say here you can see there is a body, and then we are just putting a small force on this. So, then say we are observing what will happen, whether it will restore back or it will overturn. So, that is what we will be discussing, the stability of a submerged or a floating body. So, as I mentioned, so here if we have a water in container, so we can put a body here, it is floating. So, you can see that when we give an overturn, what is whether a moment or a force is applied. So, what happens to the body, whether it is coming back or it is overturning. So, that is what we are discussing here. So, as far as the stability and equilibrium is concerned, the conditions of equilibrium can be stable or unstable or neutral. So, a body is said to be in a state of stable equilibrium if a small angular displacement of the body sets up a couple that tends to oppose the angular displacement of the body, thereby tending to bring the body back to its original position. So, here in this slide you can see here there is a fluid, and then you can see there is a body, and then a force is applied, and then a moment is given. So, it is that couple tends to oppose the angular displacement of the body and then tending to bring it back. So, here in this small experiment here you can see there is a water in a container, and then a body is floating. So, here I am just giving a small overturning moment like this, but you can see that still the body is returning to its original position by just making it stable. So, this kind of equilibrium, when a body is if a small angular displacement of the body sets up a couple that tends to oppose the angular displacement. So, this kind of equilibrium is called stable equilibrium. So, we have already seen the center of gravity and center of buoyancy. So, generally a body is said to be in stable equilibrium if center of gravity is below the center of buoyancy. So, here in this slide you can see here the center of gravity is here, and then center of buoyancy is just above that. So, if CG, center of gravity, is below the center of buoyancy, then the body is said to be in equilibrium, and then there will be a restoring couple, so that it will be unstable. And then unstable equilibrium, a body is said to be in a state of unstable equilibrium if a small angular displacement of the body set a couple that tends to further increase in the angular displacement of the body, thereby not allowing the body to restore its original position. So, this is so called the unstable equilibrium. So, here we will just see a small experiment here. So, here there is a body is floating. I am just putting a small weight upon this floating body, and then what happens is, if I am giving an overturning moment to this body here, so if say as we have seen, it is said to be stable equilibrium if it is returning back to its original position, but here when if it is overturning, an overturning couple is formed and then it is going down. So like this you can see now it is the body is said to be in unstable equilibrium, since it has gone from the previous position to a new position, and then it is say an overturning couple took place, and the body is not allowed to restore its original position. So this is so called the unstable equilibrium. So if we observe in experiments the center of gravity and center of buoyancy, when a body is floating or submerging, a quantity of liquid will be equivalent quantity of liquid will be displaced. So that center of buoyancy through where that how much liquid is displaced. So that if that center of buoyancy is below the center of gravity, then you can see that it will be generally in unstable equilibrium. So a stable equilibrium is when the center of buoyancy is above the center of gravity, and a body is said to be in unstable equilibrium if the center of buoyancy is below the center of gravity, as shown in this figure, so that an overturning couple is formed and then the floating body becomes unstable. And the third category of stability and equilibrium is the neutral equilibrium. So a body is said to be in a state of neutral equilibrium if a small angular displacement of the body does not set a couple of any kind, and therefore the body adopts the new position given to it by the angular displacement without either overturning to its original position or increasing the angular displacement. So in this case, say a body is there. So what happens is, say it is when a small displacement is given, if the body does not set a couple of any kind, and therefore the body adopts the new position is given like this. Say body, say either a floating body or submerged body in fluid statics, we can say that either the body is in stable equilibrium, or the body is in unstable equilibrium, or the body is in neutral equilibrium. So this especially when we are using in the vessels and boats while riding, the stability of the body is very important. So we will be using some of these principles as for the to determine whether the body is stable or unstable in many of the practical engineering field. So now related to this, say stability and also the buoyant force and then the center of gravity and center of buoyancy, the one important term is called the meta center for floating body. So what is meta center? So here in this slide you can see that here there is a small body or a small vessel is say floating in floating condition, and then this the center of gravity of the body is at G here, and then since it is partially submerged, the center of buoyancy is at point B here in this figure, and the body weight is indicated here as W, and then the due to the buoyant force, opposing force is there, so that is Fb, it acting in the opposite direction. So since it is in stable equilibrium, it is in condition Fb is equal to the weight of the body. So this is the situation, and now we are just giving a small displacement like this in this second figure. We are giving a small displacement to this floating body, partially floating body like this, a small displacement is given. So then you can see that this line is partially shifted in this direction, so that the new position of the body is inclined position like this, and then you can see that say due to this effect, say the weight of the liquid displaced slightly changes, and then it is say the position changes, and then the center of buoyancy shifting from B to B1. So this new position is B1, and then you can see that when if you put a vertical from B1, and then if you draw a line from say the center of buoyancy to the old position center of gravity, then those two lines will coincide at position M. So this is called the meta center, and this you can see that here a small angle is formed due to the tilt, which will be equal to this angle here. So the meta center we can define as metacenter is the point of intersection between the action of floating body passing through the points B, the center of buoyancy, and G, the center of gravity, and the vertical line passing through the new center of buoyancy. So, for an equilibrium, a body in equilibrium in floating or submerged condition, we are given a small tilt or small displacement, and then you can see that the center of buoyancy will be shifting. So, the metacenter is the point of intersection between the action of floating body passing through the points B and G, the old position, and then vertical line passing through the new center of buoyancy. So, this is generally this metacenter, and the metacenter height is generally used to see whether a body is in stable equilibrium, and also how much say vessels like a ship or a boat, how much weight it can take without any unstable problem. So, that is this importance of this metacenter. So, this metacenter height is the distance between the center of gravity G and metacenter M. So, in the previous slide we have seen, say here, this distance, say between this line and this line is the intersection is called metacenter, and the metacenter height is the distance between G to M. So, here this distance GM is called the metacenter height. So, metacenter height is the distance between the center of gravity G and the metacenter M. So, the metacenter floating bodies, it is very important we have to determine the metacenter and see what is the position of the metacenter, so that we can determine whether body is in stable conditions or unstable condition. So, here if M, the metacenter lies above G, so that a righting moment will be W into W, the weight of the floating body, GM, the metacenter height, into sin theta. So, this to make the body is said to be in equilibrium, is stable. The body is in stable equilibrium if this GM is positive, and if M lies below G, that means say in the previous slide. So, here if this M lies below G, when we are giving a large displacement and due to other problems, if M lies below G, then there will be an overturning moment, and then you can see that again this will be, this overturning moment will be W, the weight of the body multiplied by GM into sin theta, and then the equilibrium is unstable, and here GM is negative. So, with respect to metacenter also, we can say that whether there is stable equilibrium or whether there is unstable equilibrium. A stable equilibrium is when GM is positive, or when M lies above G, it is the body is said to be in stable equilibrium, and if M lies below G, then the body is said to be in unstable equilibrium. And in the case if M coincides with G, then the body is said to be in neutral equilibrium. So, this metacenter and the center of gravity of the body coincides, then we say that the body is said to be in neutral equilibrium. So, if you determine the metacenter position and metacenter height, we can determine whether the body is stable equilibrium or unstable equilibrium or in a neutral equilibrium. So, in the next slides, so let us see how we can determine this the metacenter height. So, here there is a floating body like this floating vessel, you can see, and then there is a weight put on one side of the vessel, and then we are moving this vessel from one position. Say if this is the older position of the vessel, we are moving this vessel to this body on the vessel, the small body on the vessel from one position to another. So, that there will be a small displacement will be taking place, and then we want to determine the metacenter height. So, metacenter height, as we have discussed, it is the height of we can determine if angle of tilt theta, that means with respect to the position of this body, if there is a small tilt theta caused by moving load, then we can determine that it is a distance non x across the deck is measured. So, that is the metacenter height. So, here in this case the overturning moment due to the movement of load, this load P is moving from one side to another, and if x is the distance from the old position to new position, then the overturning moment due to the movement of the load P is equal to P into x. And then say the next figure shows more clearly about this. So, to determine the metacenter height. So, this is the floating body and a small weight is placed. So, when it is in this position, it is in stable equilibrium and there is no tilt, and when we are shifting this small load to one side, you can see that there will be a tilt for the displacement will be there for the floating body like this, and then you can see that a small angle tilt, you can see this is the new position of this horizontal line. So, there will be a small angle of tilt, and then if small w is the weight of this body put here, and w is the weight of the floating body which initially passed through the center of gravity. So, the g, and then if b is the buoyancy, center of buoyancy initially, then if w is placed like in this figure, then you can see that buoyant force is equal to weight of the body, so that it is in stable equilibrium. So, now we are moving this slightly to one side, so that we want to determine the metacentric height. So, if gm is the metacentric height and w is the total weight is equal to mg including p, that means the p is the load which is moving and this mg is the weight of the floating body. So, the writing moment we can write w into gm into theta if theta is very small and theta is the angle of tilt with the horizontal. So, for equilibrium in tilted position, we can write the writing moment is equal to overturning moment. That means we are assuming it is the body is in equilibrium, then we can write writing moment is equal to the overturning moment. So, that we can write w into gm the metacentric height into theta is equal to p into x. So, where p is the load placed over the floating body, and then x is the distance between the old position and new position. So, that metacentric height finally we will get gm is equal to p into x by w into theta. So, where this w is the total weight of the body including the small weight p. So, the true metacentric height is the value of gm as theta tends to 0. So, here you can see as this theta tends to 0, here this w is this p which is indicated earlier, and capital W is the weight of the floating body, and this small w is the that is equal to p. So, this will be the metacentric, the true metacentric height is the value of gm as theta tends to 0. So, here you can see theta here in this slide. So, when theta tends to 0, that is the true metacentric height. So, for the small theta, this derivation is valid. So, that we can write gm is equal to either p in the previous figure or in this figure gm is equal to wx by w tan theta, or when theta is small we can write w theta. So, as we have seen here in this slide. So, this derivation is with respect to the previous figure here, and then say this same thing we can write gm is equal to w small wx, where this small w is the weight of this body, small body on the vessel, and then w is the total weight w. So, gm is equal to wx by w tan theta, or it is when theta is small we can write w theta as indicated in this slide. So, now like this we can determine the metacentric height. So, now we will just discuss a small example to how we can determine we will discuss a small numerical example to determine the metacentric height. So, here you can see here in this paper here. So, there is a floating body like this, and then there is a small weight is placed like here. So, we want to determine the metacentric height. So, the problem is the weight of a ship is 115 Newton. The ship's boats on one side are filled with water and weighs 0.85 Newton. The mean distance from the center of ship to the bottom boat is 8.5 meter. That means this distance from the center of the ship to the this boat which is placed here is 8.5 meter. If the angle of displacement of the plumb line theta is 3 degree 15 minutes, calculate the metacentric height. So, since this boat here is placed, this is a big ship here and a small boat is placed at 8.5 meter from the center line of the ship. So, since this ship is placed at a distance 8.5 meter, there will be a small tilt for the ship. So, that tilt is given as 3 degree 15 minutes. So, we want to determine the metacentric height. So, this problem, so here the ship is given, and here the small boat is placed at 8.5 meter, and then initially you can see if say the central line is in stable equilibrium, if the boat is not considered, then the center of gravity is here, and then the weight of the boat ship is W, which is given as 150. So, here this with respect to this position of the boat, this G is since a small weight is added, W is added, so G is shifting slightly to G dash. So, the metacentric height as per the previous derivation we have seen earlier, we can determine metacentric height is GM is equal to W, this small w, that means the weight of the boat, W into this distance x divided by W tan theta, where here this small w is the weight of the boat. So, that is equal to 0.85, and so here as we have seen that this W is capital W is total weight of the ship plus the boat. So, the capital W is equal to 150, the weight of the ship, and 0.85 is the weight of the boat. So, total capital W is equal to 150.85, and then x is equal to 8.5 meter, and theta is already given as 3 degree 15 minutes. So, metacentric height is GM is equal to Wx divided by capital W tan theta. So, here the GM, so metacentric height is equal to W is 0.85 multiplied by 8.5 divided by 150.85, that is this capital W is the total weight, the 150.85 into say tan theta, tan 3 degree 15 minutes is 0.0568. So, the 150.85 multiplied by 0.0568, from which we will get the metacentric height as 0.843 meter. So, like this a simple example, we can determine the metacentric height by placing a small weight and then we are trying to determine the metacentric height. So, similar as we have seen in the previous slides. So, in a very similar way we can determine the metacentric height for the floating bodies. So, now the next with respect to this metacentric height, we want to determine the position of metacenter relative to the center of buoyancy. So, here now in this paper here we want to determine the position of metacenter relative to the center of buoyancy. So, that is the problem. So, here you can see that there is a big vessel, and then the old position, the position is horizontal, and when there is a due to a small tilt, you can see that the new position here is say this this AA indicate, this horizontal line indicate the old position, and due to the small tilt theta, the new position is say here this inclined line. So, AC is the original water line, AC is the original water line, and A dash C dash is the new water line, and then B is the center of buoyancy in equilibrium condition. So, here you can see this B, this is the center of buoyancy in equilibrium condition, and G is the acceleration, the G is the center of gravity. So, a small tilt theta is given, and that is the angle of tilt, and then with respect to this the vessel is slightly tilted towards the right, and then A dash C dash is the displaced position for this vessel. So, now we want to determine the position of metacenter relative to the center of buoyancy. So, that is the problem. So, for small angle theta, as shown in this figure, we can write Bm, which is this distance Bm can be written as this B dash, that means this B dash divided by theta. When the angle is very the tilt angle of tilt is very small, we can write Bm is equal to B dash divided by theta. So, total weight of the fluid displaced unchanged, since we are giving a small tilt only with respect to this vessel here. So, the tilt is very small. So, due to that we can see that the total weight of the fluid displaced is unchanged, and then the weight of the wedge, we can see that with respect to this figure, the weight of the wedge with respect to the fluid displaced, this O dash is equal to weight of the wedge C dash O C dash, C O C dash. So, the weight of A dash is equal to C O C dash. And now to determine the position of the metacenter relative to the center of buoyancy, we will consider a small area A, like in this figure. Here there is a small area is considered in this figure. Here a small area is considered, and it is at a distance x from the center line O. So O is the center line, and we are considering a small area A from at a distance x from O. So now with respect to this, when the vessel is tilted, you can see that the volume set out by A, that means the small area which we have seen here, the small area, when the vessel is tilted, the volume set out by A is equal to d dash into A. So here this is the position of the small area which we are considering, and this d dash is this distance this between the old position, new position, d to d dash. So d dash multiplied by A, so that can be written as that is equal to the area, small area, into this distance x into the angle theta. So the volume set out by A is equal to Ax into theta. So now we are considering a small area. Now we will sum up all such volumes and multiplying by specific weight rho g of the liquid. We can see that here in this figure, the weight of the wedge A O A dash is equal to say A O A dash is equal to sigma x equal to 0 to A O rho g A x theta. So similarly, the weight of the wedge C O C dash we can write as sigma x is equal to 0 to x is equal to 0 rho g A x theta. So now, since as we have seen here the weight of this wedge A O A dash is equal to C O C dash, so that we can equate this weight of the wedge A O dash is equal to weight of the wedge C O C dash. So we can equate, so that we will get here rho g theta into sigma x equal to 0 x equal to Ax is equal to rho g theta sigma x equal to 0 to CO Ax. So that we can finally write sigma Ax is equal to 0, where A is the small area which we have considered and x is the distance from the center line of the vessel. So now this we can see that the sigma Ax, it is the first moment of area of waterline plane about the center line O. So this sigma Ax is the from the center line O, it is the first moment of area. So that we can say that axis O must always pass through the center of the waterline plane. So that sigma Ax is the first moment of area of waterline plane about O. So now if the couple produced by movement of wedge A O A dash to C O C dash, since we are providing a small tilt here and the vessel is tilted, so when it is the wedge, the couple produced by movement of wedge A dash to C O C dash equal to the couple due to the movement of this the resultant force R, the reaction force R from B to B dash. So the couple produced by movement of wedge A O A dash to C O C dash is equal to the couple due to the movement of this reaction R is equal to W. So the due to the movement of R from B to B dash, the new position of the center of buoyancy. So hence B dash we can calculate. So now we will take the moment of the weight of fluid set out of by area A about O. That means here the moment of weight of fluid set out by area A about O is equal to rho g Ax theta into x, since we are taking moment. So rho g Ax into theta into x. So now we can write the total moment due to the altered displacement as rho g theta sigma Ax square, the total moment due to the altered displacement. So here you can see that there is a displacement here. So with respect to this we can write total moment due to the altered displacement is equal to rho g theta sigma Ax square. So, here you can see the sigma Ax square is I, which is the second moment of area of waterline plane about the center line. So, this second moment of area of waterline is I. So, that sigma Ax square is equal to I. So, finally, we can write total moment due to the altered displacement is equal to rho, the density multiplied by g, acceleration due to gravity, into theta into I. So, the total moment due to the altered displacement is equal to rho g theta into I. So, moment due to the movement of r, finally we can write r into bb dash is equal to rho g into v into bb dash, where v is the displaced volume. So, rho g into v into bb dash, where v is the volume of the liquid displaced. So, now with respect to this, finally we can find out the Bm, that means the meta center relative to the center of buoyancy. That is what we are trying to find out. So, finally we will equate rho g v into bb dash is equal to rho g theta into I. So, finally we get bb dash is equal to this rho g will be cancelled from each side, and then rho bb dash is equal to theta, the angle of displacement, into I, the second moment of inertia, divided by the volume of the liquid displaced. So, bb dash is, here you can see this bb dash is the distance from the old position of center of buoyancy to the new position. Bb dash is equal to theta, the angle of displacement, and I is the moment of second moment of the area, and v is the volume of the displacement, the volume of the liquid displaced. So, bb dash is equal to theta I by y, and then finally we get Bm, that is what we are looking for. Bm is the distance from the center of buoyancy to the meta center. Bm is equal to bb dash divided by theta, or this is equal to I by v, where I is the second moment of area of waterline plane about O. So, finally we get Bm is equal to bb dash divided by theta, that is equal to I by v. So, this distance Bm is called as the metacentric radius. So, like this we can determine the position of meta center relative to the center of buoyancy. So, what we are doing here is, say we are considering, we are giving a small tilt, and with respect to how much liquid is displaced, and then the new position, and then we are taking the moment, and finally we get this Bm, that means the distance from the center of buoyancy to the metacentric distance as the second moment of area of waterline plane about O divided by the volume of the liquid displaced. So, that is what we are getting as, this is called the metacentric radius. So, like this we can determine the position of metacenter relative to the center of buoyancy. So, now with respect to this buoyancy, and then with respect to the meta center which we have discussed, we will discuss one more numerical example. So, here the problem is, say here you can see there is a vessel, a floating vessel, and then a small load is placed over that. So, we want to determine the maximum height of the center of gravity of this load, that means the newly placed load above the buoy or the vessel, so that the vessel remain in stable equilibrium. So, the problem statement is as shown in figure: a cylindrical buoy 2 meter in diameter and 1.5 meter height, weighing 15 kilonewton, flow in salt water of density 1025 kilogram per meter cube. Its center of gravity is 0.5 meter from the bottom. If a load 3 kilonewton is placed on the top, calculate the maximum height of the center of gravity of this load above the bottom if buoy remains in stable equilibrium. So, here a vessel or a buoy is there as shown in this figure. So, it is a cylindrical in shape, and its diameter is 2 meter, and then its height is 1.5 meter height, and then it weighs 15 kilonewton, and it is floating on salt water of density 1025 kilogram per meter cube, and initially it is stable, and then its center of gravity is 0.5 meter. Its center of gravity is this is the center of gravity is g. So, it is 0.5 meter from the bottom. So, now we are placing a load 3 kilonewton just on the center to the buoy, like this. A new load is placed to 3 kilonewton on the top. We want to calculate the maximum height of the center of gravity, that means this position of when we place a load, new load, the center of gravity will be shifting from G to G dash. So, we want to determine, we want to calculate the maximum height of the center of gravity of this load when from the bottom if buoy remains in stable equilibrium. So, this is the problem, we want to determine the new position of the center of gravity. So, here all the problem dimensions are given, and the various loads here, the buoy weight is 15 kilonewton and the new placed load is 3 kilonewton. So, here let G be the center of gravity of the buoy as shown here. This G is the center of gravity of the buoy, and then G1 is the center of gravity of the load. So, the load is placed just on the line with the at symmetric to the buoy, so that G and G1 are in the same straight line. So, G1 is the center of gravity of the load, and then G dash is the combined here. So, now a load is placed, so the center of gravity will be shifting. So, G dash is the combined center of gravity with respect to the load and then the buoy, that means 15 kilonewton is the weight of the weight of the buoy and 3 kilonewton is the load. So, with respect to that new position of the combined center of gravity, let it be G dash, and then Z is the depth of immersion of buoy, that means say this is the position of the sea water. So, the buoy is immersed to a depth of Z as shown in this figure. Z is the, it is not given, we have to find this Z. So, Z is the depth of immersion of the buoy. So, with respect to this problem statement, now the solution, let V be the volume of the salt water displaced. Since here we are placing a buoy and then extra load, there will be a liquid will be displaced. So, let V be the volume of the salt water displaced, then finally we can find out the buoyancy force is equal to weight of the salt water displaced. So, as we have seen earlier, the buoyancy is the weight of the liquid displaced. So, here in this case the buoyancy force is equal to the weight of the salt water displaced, since the buoy is placed on sea. So, this buoyancy force is equal to weight of the salt water displaced. So, that is equal to rho the density of the salt water multiplied with G the acceleration due to gravity into the volume of the salt water displaced. So, that is equal to rho into G into V. So, finally, we can write if Z is the, in this figure, if Z is the depth of the immersion of the buoy. So, we can write the buoyancy force is equal to rho into G into pi d square by 4, where d is the diameter of the buoy. So, pi d square by 4, which is the area of cross section of the buoy, multiplied by the depth of immersion of the buoy. So, finally, buoyancy force is equal to rho G pi d square by 4 into Z. So, now for equilibrium, the buoyancy force is equal to the combined weight. So, now we have the buoy weight of 15 kilonewton, and then we are putting an extra load of 3 kilonewton. So, the combined weight is equal to 15 plus 3, so that 18 kilonewton, that is equal to the buoyancy force. So, we can equate W plus W1 is equal to, W1 is the extra added weight, W is the weight of the buoy. So, that is equal to rho into G into pi by 4 d square into Z. So, we want to determine this Z, that means the depth of immersion of buoy. So, Z is equal to 4 times W into W plus W1 divided by rho into G into pi d square. So, once we substitute all the values, capital W is the weight of buoy is equal to 15 and small w1 is the added load is 3. So, 4 into 15 plus 3, then we say it is kilonewton. So, we want to determine in terms of newton. So, we are multiplied by 1000 divided by rho G is the salt water with respect to the density 1025 into G 9.81, and d square is say pi d square, 2 meter is the diameter of the buoy. So, pi into 2 square. So, that will give Z as 0.57 meter. So, we get the depth of immersion of the buoy as 0.57 meter. So, now we can say now we want to determine the center of buoyancy. So, in this figure now you can see that this Z is already determined as 0.57 meter. So, Z is 0.57 meter. So, OB is equal to half of this Z. So, that we can write this OB is equal to half of Z. So, that is equal to 0.285 meter. So, now the buoy and load is in stable equilibrium. So, as per the problem statement, the buoy and load is in stable equilibrium, and then metacenter M coincide with the combined center of gravity G dash. So, the metacenter height in this case G dash M is equal to 0. Since it is in stable equilibrium, say this metacenter M coincide with the combined CG G dash. So, M and G dash coincide, so that we can write mg dash or G dash M is equal to 0. And now Bg dash, the new position of the center of gravity G dash from to that position from Bg dash is equal to Bm. That means, since G dash is equal to the metacenter M, so Bg dash is equal to Bm, or Bg dash is equal to Bm is equal to, as per the formula which we have derived, is equal to second moment of the area I divided by V. So, or the moment of inertia I divided by V, the volume of the displaced liquid. So, here I is equal to pi d to the power 4 d to the power 4 divided by 64, pi d to the power 4 divided by 64, and the volume of displaced liquid is pi d square dz by 4. So, finally, we get Bg dash is equal to Bm is equal to this d square divided by 16 into Z. So, d is 2. So, 2 square divided by 16 into 0.57, which is the Z which we are determined. So, finally, we get Bg dash is equal to Bm is equal to 0.438 meter. So, now we want to determine the position of G dash, the new due to the added weight, the new position G dash we want to determine. So, the position of G dash is say from the bottom of the buoy, that is equal to Z dash. This is the new position of, so Z dash is equal to half Z, that means up to B, this OB plus Bg dash. So, OB is equal to half Z. So, Z dash, the position of G dash, the new center of gravity position Z dash is equal to half Z plus Bg dash. So, half Z is as we have already determined 0.285 meter plus Bg dash we have already determined here as 0.438 meter. We have already determined here, this is Bg dash 0.438 meter. So, finally, position of G dash Z dash is equal to 0.285 plus 0.438 is equal to 0.723 meter. So, now this value of the Z1, say here in this figure you can see that say to the center of gravity of the extra load G1. So, that Z1 from the bottom of the buoy, this Z1 we want to determine. So, value of Z1 corresponds to the Z dash, that means with respect to the new center of gravity we can take moments about the point O. So, here we can take moment about this particular point O, so that we can determine this Z1. So, W1 into Z1, where W1 is the weight of the buoy. So, W1 into Z1 plus 0.5 W is equal to W plus W1 Z dash. So, Z1 finally we get as W plus W1 into Z dash minus 0.5 W divided by W1. So, here in this case total weight is 15 of the buoy and 3 kilonewton of the extra load placed. So, it is 18 into 10 to the power in terms of Newton, multiply Z dash, we have already determined Z dash as 0.723 meter into 0.723 minus 0.5, W is the weight of the buoy. So, 0.5 into 15 into 10 to the power 3 divided by W1 is the extra load 3 into 10 to the power 3. So, finally, we get Z1, that means the from the bottom of the buoy to the position of the center of gravity of the extra load place as 1.838 meter. So, here finally, we have determined in this figure we have determined Z1 as 1.838 meter, and we have determined the position of G dash this Z dash we have determined as 0.723 meter. So, this gives the solution of the problem. So, now before closing this chapter, we will just have an overview of what we have studied in this fluid statics, a brief summary what we have studied in fluid statics. So, as I mentioned at the beginning of this lecture, the fluid statics is what we are studying is say what is happening when the fluid is at rest, say with respect to the forces acting, the pressure and then buoyancy, then all these things what we are studying. So, we have studied in fluid statics the principles, the fundamentals and theories have been introduced as far as this fluid statics is concerned, and then we have studied about the pressure measurements. So, we have seen that the various say methodologies like by using manometer, then we have seen the automatic gauge equipments like Borden gauges, we have seen the pressure measurement using the various equipments, and then we have also discussed the forces on submerged surfaces like inclined surfaces, horizontal surfaces, vertical surfaces, then curved surfaces. We have seen how we can determine the forces on submerged bodies, and then we have seen how we can determine the resultant forces. Say when the body is either in submerged or floating body is in a horizontal position or vertical position or inclined position, how we can determine the resultant force, and then correspondingly how we can determine the center of pressure. And then we have discussed about the buoyant forces, and we have also seen the Archimedes principles, and then how we can determine the center of buoyancy, and then with respect to its various applications we have seen in this fluid statics. And finally, at the end of this chapter we have seen with respect to buoyant forces, say when a body is submerged or when a body is floating, it can be in stable equilibrium or unstable equilibrium or neutral equilibrium. So, this also we have seen, and then we have seen with respect to the position of the center of gravity, position of the center of buoyancy, how we can define whether the body is stable or whether the body is unstable or whether the body is in neutral equilibrium. And then finally, we have defined the term meta center. If there is a small tilt is given, and then whether it is in stable equilibrium, it is trying to come back. So, with respect to a small tilt given, we have also seen what is meta center, and also we have seen how we can determine the metacentric height. So, these are some of the important topics we have discussed in fluid statics, and as we have seen in these lectures, there are a large number of applications as far as the fluid statics is concerned, starting from say with respect to the pressure measurement. Say we have seen how we can, with respect for fluid, static fluid, how we can determine the pressure measurement, and including from the how the doctor is determining the pressure, human pressure, the body pressure, how the application is there. And then also we have seen with respect to the Pascal law, how the application side, like a hydraulic lift, how it is lifting. If you put a small force, it is making, it is trying to say rise larger bodies. So, that also we have seen as applications, as in some of the previous slides we have seen. So, like this, a large number of applications are there as far as the fluid statics is concerned. So, fluid statics is one of the important branch of fluid mechanics. Say here we are since the fluid is say not in moving, it is in just static conditions. So, the analysis is much easier. So, the application, but large number of applications, as here we have already seen, man can lift the car or hydraulic lifts. So, like that various applications are there. as far as the fluid statics is concerned, and then also the ships and the movement of ships and boats with respect to its stability is very important. So the stability, the equilibrium, and then also the metacentric height, which we have discussed. It has also got a large number of applications as far as say this fluid statics is concerned. So fluid statics is one of the important branch of fluid mechanics, and here our analysis is much easier compared to fluid dynamics, since in this case the fluid is not moving, the fluid is just static, so that we can easily determine the various forces, the various say by just using the equations of equilibrium, like sigma fx is equal to 0, sigma fy is equal to 0, or sigma fz is equal to 0. That means the force in x, y, z directions, since it is static, and we can equate to sigma fx is equal to 0, sigma fy is equal to 0, sigma fz is equal to 0. And also we can take a moment, as we are doing in mechanics. Most of the principles used in mechanics are directly applicable as far as the fluid statics is concerned. So various applications, as we have seen here in various slides, there are large number of applications, and fluid statics is one of the most important branch of fluid mechanics. And the advantage here is the analysis is much easier compared to the fluid dynamics, which we will be discussing in the coming lectures. So by this we are finishing the topic on fluid statics, and next we will be discussing for kinematics of fluids, and then fluid dynamics, before going to the turbulent flow and laminar flow and other theories.